A very warm good afternoon to everyone. Myself, Dr. Pooja Kapoor, Assistant Professor at Department of Physics, School of Basic and Applied Sciences, Maharaja Aghasen University, Baddi. The topic of my lecture for today is propagation of waves in the atmosphere. We have all seen about the radio communication. In radio communication, we have a transmitting end and a receiving end. The information or the message which is to be passed is transmitted using the transmitter's antenna from the transmitting end. And then these waves are left in the space or sky and are received at the antenna at the receiving end, and then this information is extracted and is being displayed using the loudspeaker. But how do these waves propagate in the space? With that, we are going to discuss in this today's lecture. There are three types of methods using which the waves propagate in the atmosphere. The first is ground or surface wave. The second is space or tropospheric waves. It has two components, the ground reflected wave, direct or line of sight wave, and the third one, last one, is sky wave. All these types of wave propagations are being explained using this diagram. Here you can see there we have explained this ground reflected wave, the direct wave, the tropospheric wave, and the reflected sky wave also. So we'll briefly discuss all these types of propagations now. The first is ground or space waves. These waves are actually guided by the earth and follow its curvature from transmitter to the receiver. These waves are affected by the earth and are influenced by the ground characteristics. They get absorbed by the solid ground and conduct through the salty water. These operate at low frequencies and up to 1500 kilometers range. The second type of wave propagation is space or tropospheric waves. These operate within the first 15 kilometers above the surface of Earth. It has two components, ground reflected wave and direct or line of sight wave. In ground reflected wave, it travels from the transmitting antenna to the receiving antenna and is reflected by the earth towards the receiving antenna. It is not subjected to absorption by the earth's surface. It travels farther than the ground waves. The wave which is obtained in case of ground reflected wave is 180-degree out of phase or reversed in phase as compared to the input wave. The next is direct or line of sight wave. It travels directly in straight line from the transmitter to the receiver. The path is fully straight because of reflection or bending occurring in the Earth's atmosphere. Radar, microwave relays, air navigation aids in very high frequency and ultra high frequency bands rely on this type of propagation. Transmission around the globe is, however, not possible using this type of propagation. Maximum distance over which space wave is transmitted is called effective horizon. The transmission around the globe is not possible here because of the Earth's curvature. We cannot have a direct line of sight between the transmitting and the receiving antennas. The next is sky wave. It is a primarily mean of around the world or around the globe short wave communication. It is subjected to fading, change in seasons, day and night, and the atmospheric conditions. This propagation is due to the existence of electrically ionized layer of the atmosphere, which is called ionosphere. Now we will discuss about the ionosphere. Ionosphere extends from 80 to 400 kilometers above the Earth's surface. It is outer layer of the atmosphere and receives maximum energy of sun. The temperature of the ionosphere varies from 180 Kelvin to 700 Kelvin. Density is from 10 raised to power minus 5 kilometers per meter cube to 10 raised to power minus 10 kg per meter cube. Ionosphere consists of several ionized layers which are conducting. UV rays and collisions with the charged particles ionize the gas molecules. Molecules, ions, and electrons are in constant motion and collide frequently in this ionosphere. At higher points, there are few particles, the rate of recombination is low, and the gas remains ionized for longer times. Electrons present in ionosphere play an important role in the propagation of radio waves due to their small size and high mobility. At about 110 kilometers from the Earth's surface, electron concentration becomes very, very high, and this is called the Canley heaviside layer. At a height of about 250 kilometers, another belt of electrons is found, which is called aphelion layer. There are four distinct layers in the ionosphere, which are D layer, E layer, F1 layer, and F2 layer. D layer exists at the height of 70 kilometers and a thickness of 10 kilometers. It disappears at night time and reflects low frequency waves. D layer attenuates the radio waves. So the reception of sky waves is better during the night when this D layer is not present in the sky or it has vanished as compared to the daytime. F1 layer exists at 180 kilometers and it combines with F2 layer at the night time, which exists at 250 to 400 kilometers in day and 300 kilometers at night. The ionized density is very high at night. Changes in electron density and height occur with time, month, and activity of sun. These layers are effective to reflect back radio waves to the Earth's surface. The phase velocity of radio waves is greater than the velocity of light in ionosphere. That is, Vp is very, very greater than c. And the refractive index, as we all know, using Snell's law, is sin I upon sin r, which is further equal to 1 minus 81 into n divided by f square and whole under the root. The waves on penetration encounter increased electron density, so the angle of refraction increases and layers go on bending. These are some important terms which we have to discuss during the propagation of sky waves. First is the critical frequency. For the angle of incidence equal to 0 degree, the frequency which exists is called critical frequency. It is the highest frequency for which the waves sent vertically are returned back to the earth. This is also called the critical frequency. The formula for critical frequency Fc is equal to 9 into under the root Nm. It varies from layer to layer. The maximum frequency that can be used for transmission between the 2 points is called maximum usable frequency MUF. Skip distance. The minimum distance from the transmitter of radio wave and the reception which is possible by means of sky wave is known as skip distance. It varies directly with the frequency of transmission and the width of the layer. The frequency for which a given distance becomes equal to skip distance is called maximum usable frequency. Sky wave will not be received if the operating frequency is greater than maximum usable frequency. Maximum usable frequency is maximum at daytime at noon and decreases gradually. Virtual height. Sky wave traveling from transmitter T to receiver R bends gradually rather than sharply. The height of point A is called the virtual height VH and is defined as the height from which a wave sent up at an angle appears to be reflected. When the virtual height is known, it is easier to calculate the angle of incidence for a wave to return to a selected point on the Earth's surface. When the refractive index of air decreases with height much more rapidly than normal, radio waves bend towards the Earth's surface. This phenomena is called superreflection. The waves, which are reflected back by Earth's surface and again by troposphere, this happens many a time, so the range of transmission or the distance which we can cover increases. Increase in temperature and humidity leads to rise in this phenomena of superreflection. The opposite phenomena, which reduces the signal strength by bending the rays, is called subreflection. Next, we have fading. Undesirable changes in the intensity of wave which make the received signal fluctuate or fade away over a wide range is called fading. It is due to the change in electron density, roughness, ionization, and block movement of reflecting layer. Sometimes ionospheric signals may disappear altogether suddenly due to a sudden burst of ionizing radiations from the sun, leading to a sudden rise in ionization density of D layer, which causes heavy absorption of radio waves and leads to the attenuation of the signal. This phenomena mainly occurs during the daytime and is absent during the night time. Interference fading. It occurs in long distance transmission. It is produced by the reflection from the ionosphere. It causes two or more waves from the same source to travel over different paths and hence differ in their amplitude and phase. So when these different waves they superimpose on each other, the interference occurs and leads to fading. This type of fading is known as interference fading. Second is selective fading. The reflecting properties of ionosphere vary with frequency. On account of difference between component frequencies, only part of signal may fade at any given time, leading to a peculiar type of distortion in audio signals, which is called selective fading. Fading is very harmful for the radio communication, so different methods have been devised or used to minimize fading. Thank you everyone for your kind attention. I hope my lecture will be helpful for you to understand about the propagation of waves. Thank you.